My esteemed listeners, now in this session we will go through efficiency analysis of algorithms volume 2 as a sequel to efficiency of analysis of algorithms volume 1 or session 1. In session 1 and in the previous session we have talked about, or we are taken to understand, there is a way to measure the running time of an algorithm, okay, in the framework of analysis of algorithms. Okay, the running time is essentially measured in terms of order of growth of the algorithm. Okay, and we have also taken to understand, as the order of growth increases, the algorithm tend to become slow, and order of growth is, by the way, is a number. It is a number which indicates by how many times the algorithm would become slower on how many times of how many folds of increase in the input. Okay, that is essentially the meaning of order of growth. So at this juncture we have taken to understand, or we are in the hold of the knowledge that says that algorithm running time can be measured, may not be in seconds, but as a measure, as a metric in terms of order of growth. Okay, but order of growth alone will fail to express the running time of an algorithm, because it also depends upon the kind of the instance of the problem, the nature of the instance of the problem, how exactly the example of the problem resides. Okay, how exactly example of the problem will appear. So it also, or in other words, simply told, it also depends upon the texture of the input, the nature of the input. We will take some exemplars to explain as to what do we mean by the cases of efficiency. An algorithm may enjoy best case of efficiency, it can enjoy the worst case of efficiency, it can suffer from worst case of efficiency, or it can be an average case of efficiency. Whether an algorithm enjoys being in the best case or in the suffers from worst case or average case depends upon the nature of the input. As an example, if you take linear search, we are searching for a key. Okay, if the key exists among n number of elements, let us say 1000 in number, if the key exists right in the very first place, the number of comparisons happens to be only 1. And if it happens to be existing at the end, and you need to do n number of comparisons, you need to do 1000 comparisons if it is a 1000 element array. And if the key is not at all present, then also you need to compare for 1000 times, provided the array is not sorted, of course. But throughout this course, we just going to analyze any algorithm that is presented for its worst case efficiency, and we will define as to what do we mean by best case efficiency and worst case efficiency, and also average case efficiency, and we will also give examples. Okay, best case efficiency is the input size of the instance, or input size of the problem for which the algorithm runs for the fastest possible time. And the worst case efficiency is the input size, once again, for which the algorithm runs for longest duration of time. And average case efficiency stands in between. It is neither the best case nor the worst case, and it depends upon the nature of the input. Input may appear like anything. Okay, it can be any way, any phase of the input. And we will continue with this linear search. So for best case efficiency, the key is there in the very beginning cell and the very first cell, and the key is there in the last cell, or key is not at all there. This will present the worst case, and key may be anywhere. Okay, key may be in the midst, key may be in the first quarter, key may be in the third quarter. We don't know. The input is non-deterministic. In such case, for such cases, we will always deal the efficiency under average case. But throughout the course, we will just analyze all the algorithms that are presented to us for their worst case, because it is always worst case which will consume maximum number of time, maximum amount of time, maximum time will be expended only for the worst case of the worst case efficiency of the algorithm. Okay, we will take literally an example of linear search, and this is the way we write the algorithm linear search. This is the name of the algorithm, which will be written in camel case representation. These are all the parameters, an array and a key. Okay, two parameters are supplied, and since an algorithm is to be presented in a most unambiguous way, and we will present as to the first comment is as to what it will do. Okay, it will search for the given input value, what the algorithm does. Okay, this is the first step, first comment. Okay, searches for a given input value in a given array by linear search. The input presented to this is an array a 0 to n minus 1 and a key to be searched. The array is unsorted. I think I should have added here unsorted. The array is unsorted. Okay, it is not sorted, because if it is sorted, it will present a different scenario altogether. Okay, it takes no time to search anything. Okay, output, the index of the first element of array A that matches the key, or minus 1 if there are no matching elements. Okay, we will start with this initialization. I is set to 0, while I is less than n. Okay, it has to go up to n minus 1, comparing, and A of I is not equal to key. Okay, if both the conditions match, this condition and this condition, you can make a jump. You will go to next element. You will go to next element. When one of the things is not matched, either we have reached the end or key is found. I is less than n still, but A of I equal to key. Then this won't be incremented. This won't be incremented. The control will come over here. And if the key is found somewhere in between, I will be definitely less than n. Therefore, it will return the location where this key was found. Okay. Otherwise, if the key is not there, it will complete the complete iteration. It will complete the complete comparison. Okay. The while loop will be completely over. Then it will come, and unable to find the key, it will return 1. Okay. This is the thing that this is the algorithm. Now we will discuss about the worst case and the best case for this. Okay. The best case is key being present in the very first place. Therefore, number of comparisons it would take is only 1, because the basic step there in the algorithm is comparison. The basic step is comparison. This comparison. Okay. Therefore, it will take only 1 comparison if it is found in the very first place. Okay. The best case is defined yet again here, is the input size n corresponding to which the algorithm runs for the shortest possible time for all possible inputs. Okay. Worst case, key being present in the last place or key is not at all present. Okay. Number of comparisons it would take is n. Okay. All the elements must have been compared. Therefore, the worst case of an algorithm may be defined as an input size n corresponding to which the algorithm runs for the longest possible time for all possible inputs of the same size. Okay. This thing. Average case efficiency. See, average case efficiency is dealt or is done for an algorithm for an instance which is non-deterministic in nature. So here, anyway, this problem presents a very simple scenario as far as average case efficiency is concerned. In complicated algorithms, for complex problems, it is really tough to estimate the average case efficiency, because it involves non-deterministic nature of the input pattern. Therefore, it involves probability, because non-deterministic things or imprecise things or ambiguous things can also only be dealt with under the realm of probability. Okay, it should be dealt under probability theory. Anyway, we will take an example. For the sake of completeness, we will just analyze the linear search algorithm for its average case efficiency. Let P be the probability of success. Okay, the key may be found either in the first place or in the second place or in any places. Therefore, every place will enjoy the probability of key, if it is present, to be P by n. So every step or every cell or every location, if the key is found, they will enjoy the probability of being found is P by n. If the key is not found, then the probability of your searching mechanism happens to be 1 minus p. Okay, 1 minus p. P is probability, 1 minus p is reliability. Opposite of probability is reliability. Okay, then we will just calculate. see average number of times a basic operation is getting executed as a function of input size is given by, if it is found in the very first place is only, then only one comparison will take place. It is 1 into p by n, probability of a key being present in the first place, and 2 comparisons will have been done by the time you find the key in the second position. Therefore it is 2 into p by n, like this, n into p by n, and this addresses if key is found anywhere within n, okay, and this addresses the key if the key is not found, okay. Either this will be true or this will be true, okay. Anyway, we will just put p equal to 1, okay. We will put p equal to 1 here, sorry, here we will put p equal to 1, then it is a success, okay. And we have taken out p by n as a common factor, and we have arranged this series. This becomes an arithmetic series, okay, and p by n is taken as a common factor, and the sum of this series is given by the formula 1 to n is given by n into n plus 1 divided by 2, and this remains as it is without any simplification. It's not required. If it is a success, we will put p equal to 1, then this will become 0. Since it is a success, it is not a failure. So 1 by n into n plus 1 divided by 2, n and n will get cancelled away, and we will be left with n plus 1 divided by 2. Therefore average case efficiency of linear search algorithm is n plus 1 divided by 2. If it is a failure, that is key is not found, then p will be substituted with 0 value, and then it will become n, then it will become n. Here it will become 0 because the numerator becomes 0. Therefore average number of comparisons, okay, for failure is it is n number of comparisons will have taken place, okay. Now we will come to a very important topic in efficiency analysis of algorithms, that is giving asymptotic notations for the algorithms, okay. Up till now and unto this point, we are of the notion that the algorithm running time can be measured with the help of order of growth, with worst case complexity or worst case efficiency attached. So worst case efficiency and order of growth. But if a problem is given to let us say a group of people, say 15 number, and if they are asked to write the algorithm, they will come out with different algorithms for the same problem. And if you happen to measure, if you happen to take the count of steps, basic steps that have been executed in every algorithm, it presents a complex picture, okay. One giving C of n equal to n square, other person will be giving C of n equal to n cube, and some other person may be giving C of n equal to 2n cube plus 2n square plus 10n, something like this, because it is a notion they must have written in a different way, okay, and arriving at the running time of the basic step, a number of times the basic step is getting executed to be a complex formulation, because you have seen while we found out order of growth, C of n happens to be some kind of a function. It can be n cube, or it can be 2n square, or anything depending upon the nature of the algorithm, depending upon the strategy used, depending upon the way in which the problem has been solved, okay. Therefore in order to avoid this drudgery, then it becomes very tough to find the order of growth, because we have to neglect the lower order terms and we have to consider only higher order term, okay, and then we have to simplify. So it becomes obtaining some kind of a wholesome function, this C of n, becomes tough. Therefore scientists or mathematicians or algorithmists have arrived at 3 kinds of notations which are asymptotic in nature, okay. They grow parallelly. Asymptotic means they grow parallelly. So your algorithm, so you have to come to an understanding that your algorithm will be given some kind of a certificate of merit, a certificate of ranking. Your algorithm will be ranked. It could be ranked under bigO category, or it could be along big omega category, along big theta category, okay. These are all the names of the sets, okay. These are all the names of the sets. In bigO set, the set is named as bigO set. You will find the algorithms which are existent, okay. to the same problem written by somebody else maybe, okay, which will run as slow as your algorithm, or your algorithm will run as slow as the algorithms available in this set. In the same token, there is another set called big omega, where there exists algorithms which are as fast as your algorithm. Big theta will present some kind of a tight bond. Okay, by attaching your algorithm under big theta category, you are implying that there exists algorithms which are slower than your algorithm and which are faster than your algorithm, and you are in between. Your algorithm is in between. Therefore, you are fixing a tight bound for your algorithm. Okay, big O presents an upper bound for your algorithm, and big omega will present a lower bound for your algorithm, and big theta will provide some kind of a tight bound for your algorithm. Okay, we will continue. We'll continue in dealing with this big O and big theta and big omega in a detailed way. Okay. And you will see some kind of an asymptotic nature of this curve. Okay, they are growing parallelly. Okay, this is your algorithm. Okay, this is n value, the input value goes along x-axis, and running time of the algorithm goes along y-axis. Okay, as the n value increases, naturally as the input size increases, naturally the consumption of time, running time, should also increase. Okay, running time is this vertical line. So here it is increasing, and there are this blue lines indicates the algorithms that are existent in a set called big O, which are, okay, these algorithms, or your algorithm is running parallelly as slow as the algorithms found in big O. That is the thing. But before you prove that your algorithm can be attached to big O category, you need to follow certain formalities. Okay, you are developing by putting a metric, by ranking your algorithm under big O category, you are trying to bring some kind of a formalism. You are trying to develop some kind of a formula. Okay, you are trying to develop some kind of a mapping function, whatever you can tell. Okay, whatever you can express. So big O notation is explained over here. You need to remember this definition, and if you remember one definition, you can just tweak the other definitions, okay, to be befitting. A function f of n, okay, that is your algorithm. Okay, function f of n. Okay, this represents the running time of your algorithm. Okay, is said to belong to big O of g of n. Okay, set of algorithms called g of n in a set called big O, denoted by f of n belongs to big O of g of n if and only if f of n has an upper bound defined by some constant multiplier c, okay, of gn for all large values of n. Okay, large values of n. This should be n, actually n naught. This can be called as n naught. That means, yeah, I will complete this definition and I will come back again. There exists some positive constant c and some non-negative integer n naught, such that f of n, that is your algorithm, the algorithm that is developed by you, is less than or equal to, in terms of running time, of course, in terms of running time, c times g of n for all values of n greater than or equal to n naught, beyond this input size, your algorithm runs little faster when compared to algorithms which are existent in big O set. Okay, behind this, okay, or lesser than this value of n naught, your algorithm must be consuming little bit more time when compared to the algorithms that are existent in big O. Like that, there is an undulation, but anyway it is below the value of n naught. Therefore, this you can forget. Okay, don't mind about these values which are lesser than n naught. Beyond n naught, your algorithm is as slow as the algorithms that are existent in big O, or it may be little faster when compared to the algorithms that are existent in big O. That is the meaning of this. Okay, you will be, I think there are examples given to you. You may be asked to prove that your algorithm has a complexity expressed by something like this, time complexity 15n or 10, 15n plus 1. plus 10. This is actually running the number of times the basic operation is getting executed. Okay, I would say looking into this higher order term, I would say this belongs to big O of n square. I need to prove this. I can prove if and only if I find the appropriate value of c, that constant multiplier, and n naught. Okay, so I will just align this. 15n plus 10 is greater than or equal to 15n plus 10. 15n square plus 10, let us say 15n square plus 10, or 25n square. Okay, 10n square, you can tweak this. Okay, 25n square, you can make this compact. 25n square is definitely greater than or equal to 25n for some values of n. Okay, if substitute n equal to 1, okay, 25n square is greater than or equal to 25n. Therefore, beyond 1, this will surpass. Okay, this will tend to be slower when compared to this. Okay, therefore here c is 25 and n naught is 1. Okay, therefore f of n is less than or equal to 25n square, or f of n belongs to big O of n square within constant multiple, that is to 25, and n naught greater than or equal to 1. But we can exercise the flexibility. We need not have to do like this only. We have to concisely reduce this given function, that is your algorithm function, into a crisp or a single term preferably, because you will be neglecting lower order terms. Here there is a flexibility to tweak the given function. Say if f of n is less than or equal to 15n square, you can make it 15n square only, retaining f of n as it is. For n not equal to 1, f of n is greater than 15n square. Okay, f of n is greater than 15n square. For n not equal to 2, it will be 15 into 2 here, 15 into 2 plus 10. Okay, 40, but 15n square is 15 into 2 square, that will become 60. Therefore 15n square is little slower when compared to 15n square, 15n plus 10, that is your algorithm. Therefore f of n may said to belong to big O of n square, provided c becomes 15 and n naught is greater than or equal to 2. Okay, similarly we will explain big O omega notation. Big O omega notation will take your algorithm little above the algorithms that are existent in a set called as big omega. Big omega, that means your algorithm tend to be little slower or little slower, or it is tend to be as fast as this algorithm. The better word is as fast as. Okay, because traditionally the algorithms that are placed in big omega notation will be faster when compared to the algorithm that is set to be compared with another algorithm. A function f of n, we will come out through this definition. You can notice same thing, okay, and changes here and there. A function f of n is said to belong to big omega of g of n, denoted by f of n belongs to big omega of g of n if f of n has a lower bound. There we said upper bound, here we say lower bound, defined by some positive constant c. Here c is here, positive constant c, okay, positive constant multiple of g of n for all large value of n. Okay, this is n naught actually. Okay, this is n naught, beyond which this condition holds good. F of n, the time taken for my algorithm is greater than or equal to, okay, anyway it's moving asymptotically parallelly to this. Okay, the algorithms that are existent in big omega, c times g of n. Okay, f of n is greater than or equal to c times g of n for all values of n greater than or equal to n naught. So we have taken two examples over here to prove f of n. The question will be something like this: f of n is n cube plus 2n square. Okay, let us see where to fit this as far as big omega is concerned. Okay, is greater than or equal to 3n square. I have taken consider the lower order term. Okay, it is lower than n cube, higher order. Anyway, for fixing big omega or big O or big theta, we need to look at the higher order term. Therefore the next lower order term for n cube is n square. Therefore I have just adjusted this. Okay, it should be greater than 3n square. Go on substituting the value, put n equal to 1, this will be 1 cube plus 2n square, 2 into 1, so 1 plus 2, 3, and this is 3n square. Put n equal to 2, so this will be 8, this will be 8 plus 2 times 4, so 6, 8 plus 6 is 14, and this will be 3 into 3 into 4, 12. 3 into 4, 12. So upon n naught greater than or equal to 1, your algorithm tend to be slower when compared to this algorithm. Okay, this is 3n square. Here C is 3, and you can very well write the algorithm f of n belongs to big omega of n square. That's it. That's it. So people will understand as to what the value of C is. Okay, and we anyway, to prove, we need to find out C as well as n naught. Okay, therefore f of n belongs to big omega of n square, where C equal to 3 and n naught is greater than or equal to 1. And there is another algorithm with a running time given by f of n equal to n square plus 3n. Okay, the next lower term for n square is n log n. Therefore, it should be greater than or equal to 3 times n log n. 3 times n log n. Okay, 3 is assumed. Okay, you assume that both of them are 3. Okay, 3. Only this term is considered. This term is neglected. Okay, lower order term is neglected. In place of this thing, I have taken some coefficient. Okay, in order to prove 3 n log n. So therefore, n naught is greater than or equal to 1. You put n equal to 2. N equal to 2. You will get 2 square. That is 4. 4 plus 3 into 2. 4 plus 6. 10. Here 3 into 2 log 2. Log 2 is 1. So okay, 3 into 2, 6. So this has given you 10 and this has given you 6. Therefore, it can be said that f of n pertains to, or f of n belongs to big omega of n log n. Here C equal to 3 and n not equal to 4. Right. Then big theta notation. A function f of n is said to be in big theta g of n denoted by f of n belongs to big theta of g of n if f of n is tightly bounded both by upper and lower bounds. Here is upper bound and this is the lower bound. Okay, that are defined by some positive constant multipliers of g of n for all large values of n. This also implies that there exist some positive constants C1 and C2, C1 for the lower bound and C2 for the upper bound, and some non-negative integer n naught here, beyond which this definition holds good. Okay, therefore my algorithm is here. Okay, tightly bounded. It is greater than or equal to C2 of g of n. Okay, and lesser than or equal to Cg of n. C2 of g, C1 of g of n. It should be C2 of g of n. Yeah, C2 of g of n. And it should be greater than C1 of g of n. Yeah, now this is correct. And we will take one example to prove as to how to arrive at this big theta notation. Usually throughout the course we will analyze the algorithm for its worst case complexity and we will give the ranking in terms of big theta, because big theta is some kind of neutral, and big theta accepts that there exists a group of algorithms which are as slow as my algorithm, your algorithm, and as fast as our algorithm. Okay, and we are tightly bound. So if our algorithm is something like this, f of n is equal to 2n square plus 2n. Okay, and I will say f of n is definitely lesser than or equal to 4n cube, 2 plus 2 n cube. Next higher order term is n square. For n square it is n cube, so it comes over here. Okay, now I will go on substituting value for n. If n equal to 1, this will be 2 plus 2, 4. If n equal to 1, this will also be 4. If n equal to 2, this is 4 into 2, 8, and 2 into 2, 4, 8 plus 4 is 12, and here it is 4 into 2 cube, 4 into 8, it is 32. So this exceeded. Therefore we can say, so therefore n naught becomes greater than or equal to 1 and C1 equal to 4. Then definitely this can be said to belong to big O of f of n cube, big O of n cube. And as far as this is concerned, okay, the next lower term is n log n. So this can be said to be greater than 4 times n log n. Okay, so now we are talking about the lower bound for n log n. For n not equal to greater than or equal to 1, you take take n equal to 2. N equal to 2. This is 2 into log 2. Log 2 is 1. Therefore 2 into 4. 4 into 2 is 8. And as far as this is concerned, substitute 2 over here. 2 into 2 is 4. So 4 into 2 is 8. And 2 into 2 is 1. 2 into 2 is 4. So 4 plus 8, 12. Therefore, f of n is greater than 4n log n for n naught greater than or equal to 1 and C2 equal to 4. Here it is C2. So therefore, C1 for this algorithm is, okay, in order to make it to big O, so f of n belongs to big O of n cube provided C1 equal to 4 and n naught is greater than or equal to 1. Okay, and f of n can also have a lower bound, which is big omega of n log n. Okay, n log n. In this case also, okay, C2 equal to 4 and n naught is greater than or equal to 1. So with this discussion we have understood that not only order of growth is important, but the texture of the input also matters, and we need to always analyze an algorithm for its worst case complexity. Okay, and trying to find order of growth for all the algorithms that is written to solve a problem is a excruciating thing. It's a very drudgery. Therefore we will assign some kind of a metric, some kind of a ranking for our algorithm. This ranking comes in 3 groups, that is big O, big omega and big theta. Big O and big omega, big theta. Big O will provide our algorithm with a higher bound, telling that there exists a group of algorithms which are as slow as my algorithm, as our algorithm, and big omega will put our algorithm into a upper bound, into a lower bound, because we will be as well telling that there exists an algorithms which are faster than my algorithm or as fast as my algorithm. And big theta, by giving a ranking under big theta category, we are putting both the bounds, okay, both upper bound and lower bound, and our algorithm will experience some kind of a tight bound. Okay, and if you are given, if you are 40 people or 50 people are given to write algorithms for a problem, they will come out with different solutions. And if you can assign big theta, and whichever the big theta, whichever the ranking enjoys lower order of growth, that algorithm will be selected. Therefore, we reduced by attaching the algorithms into some kind of a ranking orders or asymptotic notations. We have reduced the drudgery of calculating order of growth for each and every algorithm. Okay, with this we will conclude efficiency analysis of algorithms into 2, and we will move with some examples, okay, varieties of examples in our 3rd session, wherein we will find out big theta complexity or asymptotic notations for the given algorithms. Okay, we will analyze the algorithms and we will fit these algorithms under big theta category. So with this we will conclude. Until then, bye my esteemed listeners. Okay, I will come back again with efficiency analysis of algorithms part 3.